New Horizons, launched January 19, 2006, is the fastest spacecraft ever built for planetary exploration. It rocketed away from Earth at 36,400 miles per hour, fast enough to reach the Moon in just 9 hours, making it the first spacecraft to achieve Earth escape velocity directly from launch. As of January 2026, it's traveling through the Kuiper Belt at 32,000 miles per hour, over 5.8 billion miles from Earth. That's 62 astronomical units. 62 times farther from the Sun than Earth is. But here's the paradox: despite being built with technology from the early 2000s, computers with processing power equivalent to a PlayStation 2, cameras with less resolution than a 2010 smartphone, and despite being so far away that radio signals take over 8.5 hours to reach Earth, New Horizons still transmits science data every day. Crystal clear measurements from a region of space more distant than any spacecraft has ever studied in detail. How is it possible to communicate across nearly 6 billion miles with a 12-watt transmitter? And how much longer will we be able to keep this fragile connection alive before New Horizons drifts into permanent silence? The answer reveals one of NASA's most audacious gambles, and one that's now facing an uncertain future. When NASA began planning a mission to Pluto in the 1990s, engineers faced what seemed like an impossible problem. Pluto orbits 3.7 billion miles from the Sun, so far that sunlight takes over 5 hours to reach it. Any spacecraft using conventional rocket propulsion would take 30 to 40 years to get there. By the time it arrived, the mission team would have retired or died. But there was a window. A rare opportunity. In 2006, Jupiter would be positioned perfectly to act as a gravitational slingshot, a massive cosmic accelerator that could cut the journey time in half. If NASA could launch by January 2006, the spacecraft could reach Jupiter in just 13 months, use the giant planet's gravity to boost its speed, and arrive at Pluto by 2015. Just 9 years total. Miss that window, and the next favorable alignment wouldn't occur for another decade. But here's the counterintuitive detail: New Horizons wasn't supposed to study the Kuiper Belt. The mission proposal, submitted to NASA in 2001, requested funding only for a Pluto flyby. The Kuiper Belt, a vast region beyond Neptune containing billions of icy objects left over from the solar system's formation, wasn't even mentioned in the primary mission objectives. The spacecraft would fly past Pluto, transmit its data back to Earth, then drift into the outer solar system with nothing left to do. The original plan was simple: 9 years to reach Pluto. One intense flyby lasting just a few hours. Then the mission would end. Nobody expected New Horizons to still be operational in 2026, 20 years after launch, making groundbreaking discoveries in the most distant region of the solar system any spacecraft has ever studied. On July 14, 2015, at 7:49 a.m. Eastern Daylight Time, New Horizons screamed past Pluto at 31,000 miles per hour, coming within 7,800 miles of the dwarf planet's surface, closer than the distance from New York to Tokyo. For 9 years, the spacecraft had been racing through space. Now it had just 9 minutes in Pluto's close vicinity to capture everything. The results revolutionized planetary science. New Horizons revealed Pluto's iconic heart, a massive plain of nitrogen ice called Sputnik Planitia, 600 miles across, constantly churning like a lava lamp as warmer ice from below rises and cooler ice sinks. The spacecraft discovered mountains of water ice reaching 11,000 feet high, as tall as the Canadian Rockies, on a world where temperatures reach -400 degrees Fahrenheit. It found evidence of a liquid water ocean beneath Pluto's frozen surface, glaciers of nitrogen flowing across ancient impact craters, and a hazy blue atmosphere layered like Earth's but made of exotic organic compounds. New Horizons photographed Pluto's largest moon Charon in unprecedented detail, revealing a dark polar cap nicknamed Mordor Macula, made of reddish organic material, and a network of canyons stretching 1,000 miles across its surface, evidence that Charon's entire subsurface ocean froze and cracked the moon's crust as it expanded. The spacecraft captured images of Pluto's smaller moons Nix, Hydra, Kerberos, and Styx, tiny irregular chunks of ice tumbling chaotically through space, likely fragments from an ancient collision that formed Pluto's moon system. Then, in January 2019, New Horizons performed humanity's most distant planetary flyby, a close encounter with Kuiper Belt Object 486958 Arrokoth, 4 billion miles from Earth. Arrokoth looked like nothing humanity had ever seen, a contact binary, two lobes of ancient ice gently merged together like a cosmic snowman, 22 miles long, spinning slowly through space. The flyby revealed that Arrokoth formed through gentle accretion, small particles of ice sticking together over millions of years, not violent collisions as many theories predicted. Its pristine surface showed almost no impact craters, suggesting the outer Kuiper belt is far less chaotic than astronomers expected. The discovery fundamentally changed our understanding of how planets form. After Arrokoth, New Horizons had fulfilled its extended mission objectives. But the spacecraft kept flying. And that's when the mission diverged into two parallel paths that reveal something profound about exploration itself. Path 1, Planetary Science. This is what New Horizons was built for. The spacecraft's cameras, LORI, Long-Range Reconnaissance Imager, and MVIC, Multispectral Visible Imaging Camera, continue photographing Kuiper Belt objects from distances impossible to achieve from Earth. Since 2019, New Horizons has observed 36 KBOs from ranges as close as $0.10, 9.3 million miles, revealing shapes, colors, and rotation rates that ground-based telescopes can barely detect. The spacecraft's LASA infrared spectrometer analyzes the composition of these ancient objects, determining whether they're made of water ice, methane ice, nitrogen ice, or exotic organic compounds. Each observation reveals clues about the early solar system, what the primordial disk looked like 4.6 billion years ago before planets formed. Path 2, Heliophysics. This is what New Horizons has become. 3 instruments, SWAP, Solar Wind Around Pluto, PEPSI, Pluto Energetic Particle Spectrometer Science Investigation, and SDC, Student Dust Counter, run continuously, measuring the charged particle environment and dust distribution in the outer solar system. These measurements are unique. Voyager 1 and 2 are in interstellar space beyond the heliopause. Pioneer 10 and 11 are dead. New Horizons is the only active spacecraft currently operating in the outer heliosphere, the region where the Sun's influence is still strong but weakening, creating a transition zone between the solar wind and interstellar space. Right now, as of January 2026, New Horizons has traveled 62 Australian dollars from the Sun. This may not seem like much, it's still technically within the Kuiper Belt, which extends to roughly 50 Australian dollars for classical KBOs but includes scattered disk objects out to 100 Australian dollars or more. But imagine you've lived your entire life in a city. You've never left the urban core. Then one day, you drive out past the suburbs, past the farmland, past the last gas station, until you're on a dirt road surrounded by wilderness with no streetlights, no cell service, no sign of civilization anywhere. That's where New Horizons is now, in the remote frontier of our solar system, far beyond where any active spacecraft has made detailed scientific observations. The spacecraft is measuring phenomena that Voyager never studied because Voyager rushed through this region too quickly, focused on reaching interstellar space. New Horizons is taking its time, examining the heliosphere's structure in a way no mission has done before. Before we go further, let's clarify two terms that people often confuse, the Kuiper Belt and the Oort cloud. The Kuiper Belt is a disc-shaped region beyond Neptune's orbit, extending from roughly 30 Australian dollars to 50 Australian dollars from the Sun. Think of it like the asteroid belt between Mars and Jupiter, but much larger and filled with icy objects instead of rocky ones. Pluto is the most famous Kuiper Belt object, though thousands of others have been discovered. The Kuiper Belt is relatively flat, aligned with the plane of the planet's orbits. The Oort cloud, on the other hand, is a theoretical spherical shell of icy objects surrounding the entire solar system, extending from roughly $2,000 to $100,000, halfway to the nearest star. Think of it like a vast cosmic bubble enclosing everything. The Oort cloud is thought to be the source of long-period comets, those that take thousands of years to orbit the Sun. No spacecraft will reach the Oort cloud for tens of thousands of years. So when did New Horizons cross from one region to another? The exact moment was October 1, 2024, when the spacecraft reached $60, double the distance Pluto was when New Horizons flew by in 2015. At this distance, New Horizons officially entered the outer Kuiper Belt/scattered disk region, where objects are more spread out and sunlight is just 1/3600th as bright as it is at Earth. Scientists knew they'd crossed this threshold because the spacecraft's dust counter detected a measurable change in particle density. The region beyond $50 has fewer small dust grains. Most have been swept out by radiation pressure and planetary gravitational interactions over billions of years. What remains are larger, older particles and the occasional pristine KBO. The significance of this milestone cannot be overstated. New Horizons is exploring a region that contains the solar system's most ancient, most pristine material, objects that have barely changed since they formed 4.6 billion years ago. Every measurement adds to humanity's understanding of where we came from. To put this in context, here's a multi-stage timeline. From launch in January 2006 to Jupiter flyby in February 2007 took 13 months. From Jupiter to Pluto, July 2015, took 8.5 years. From Pluto to Archaeoth, January 2019, took 3.5 years. From Archaeoth to $60, October 2024, took 5.75 years. And from $60 to the projected end of the Kuiper Belt around 2028 to 2029 will take approximately 4 to 5 more years. New Horizons has spent more time exploring the Kuiper Belt than it spent traveling to Pluto. Here's the core mystery at the heart of New Horizons operation. How does a spacecraft 5.8 billion miles away, built with early 2000s technology, still talk to Earth? Let's start with the transmitter. New Horizons has a 7-foot diameter high-gain antenna mounted on the front of the spacecraft, always pointed at Earth. The antenna transmits in the X-band frequency at 8.4 GHz, with a power output of 12 watts. For comparison, a typical incandescent light bulb uses 60 watts. A standard LED bulb uses 10 watts. New Horizons signal, the one carrying scientific data across billions of miles, draws less power than the light in your bathroom. Now consider the distance. As of January 2026, New Horizons is 5.8 billion miles from Earth. That's 62 astronomical units. Let's use a perspective ladder to understand that scale. The Moon is 238,000 miles from Earth, about 1.3 light seconds. New Horizons signal takes 8 hours and 36 minutes to reach Earth, over 23,000 times farther. Mars at its closest approach is 34 million miles from Earth, about 3 light minutes. New Horizons is 170 times farther than that. Neptune, the most distant planet, orbits at an average distance of 2.7 billion miles from the Sun. New Horizons is now more than twice as far from the Sun as Neptune. When New Horizons transmits a signal, that signal spreads out in all directions following the inverse square law. By the time it reaches Earth, the 12-watt transmission has expanded across a cone billions of miles wide. The received signal strength at Earth is approximately 0.000000000000000001 watts, 100 quadrillionth of a watt. To put that in perspective, if you collected all the radio energy New Horizons has transmitted to Earth over its entire 20-year mission, it wouldn't be enough to warm a cup of coffee by 1 degree. So how do we hear it? The receiver must be massive. NASA's Deep Space Network operates 3 facilities spaced equally around Earth, at Goldstone, California, Madrid, Spain, and Canberra, Australia. Each facility has multiple antennas, but New Horizons primarily communicates using the 70-meter dishes, antennas 230 feet in diameter with collecting areas over 38,000 square feet. These are among the largest antennas on Earth. The dish at Goldstone, California, DSS-14, is so sensitive it can detect a signal from New Horizons equivalent to a 20-watt light bulb shining from 13 billion miles away. Because New Horizons is traveling away from Earth along a specific trajectory, it remains in roughly the same direction in the sky. As Earth rotates, the 3 DSN stations work in relay, ensuring New Horizons always has a ground station in view. At any given moment, at least one antenna is listening. Commands are uploaded approximately once per week. Science data downloads continuously during scheduled communication windows. The data rate has declined dramatically as distance increases. At Pluto in 2015, New Horizons could transmit at 1 kilobit per second. Today, at 62 Australian dollars, the spacecraft transmits at just 600 bits per second, roughly equivalent to a 1990 dial-up modem connection. A single high-resolution image that took minutes to transmit from Pluto now takes hours to download from the Kuiper Belt. But here's the challenge New Horizons faces: unlike Voyager, which uses radioisotope thermoelectric generators, RTGs, that decay slowly over decades, New Horizons relies on a single RTG that's now operating far below its design specifications. When most space probes run out of power, they die. New Horizons launched with a single GPHS RTG, General Purpose Heat Source, radioisotope thermoelectric generator, fueled by plutonium-238. At launch in 2006, the RTG produced 245 watts of electrical power. Enough to run the spacecraft's computer, transmitter, instruments, heaters, and all other systems with power to spare. But plutonium-238 has a half-life of 87.7 years. Every year, the RTG produces slightly less power as the plutonium decays. It's not a switch that flips off, it's a slow, inexorable decline. By 2015, during the Pluto flyby, power output had dropped to 202 watts, about 82% of launch capacity. As of 2026, the RTG produces approximately 185 watts and declining at a rate of about 4 watts per year. Here's why this is critical: New Horizons doesn't have enough power to run all its systems simultaneously. The engineering team has been managing this power crisis since before the Pluto encounter. The spacecraft operates in different modes depending on what it's doing. During hibernation, when New Horizons is essentially sleeping, only essential systems remain active: the computer, the transmitter broadcasting a weekly beacon signal, and 3 instruments, SWAP, PEPSI, SDC, that collect data continuously. Power consumption in hibernation, about 175 watts. During active science campaigns, when New Horizons wakes up to photograph Kuiper Belt objects or transmit stored data, additional systems activate: cameras, spectrometers, the main transmitter at full power. Power consumption during active mode, over 200 watts. The engineering team has implemented aggressive power conservation measures. They've disabled non-essential heaters, allowing parts of the spacecraft to drop to -400 degrees Fahrenheit. They've shut down redundant systems. They've optimized the computer's power management algorithms to squeeze every possible watt from the declining RTG. But eventually, they'll run out of things to turn off. The most emotionally devastating moment came on October 25, 2016, the last time New Horizons used its LORRI camera to photograph Pluto from a distance. The image showed the dwarf planet as a tiny speck, barely a few pixels across, receding into the distance. Then LORRI was shut off to conserve power during the long cruise to Arakath. When the camera was reactivated in 2018 for the Arakath encounter, it had been dormant for over 2 years, the longest any spacecraft camera has been powered down and successfully revived in deep space. Today, New Horizons operates with just 5 scientific instruments intermittently active, 3 of which run continuously. The spacecraft spends most of its time in hibernation to conserve power. Active science campaigns occur only a few times per year, brief windows when New Horizons wakes up, observes a distant Kuiper belt object, then goes back to sleep. And the power continues to decline. At the current rate, engineers project New Horizons will have insufficient power to operate even a single instrument and maintain communication by the late 2030s. After that, the spacecraft will still be flying, it will continue traveling through the outer solar system for millions of years, but we will no longer be able to hear it. New Horizons' 20-year journey has been remarkably smooth, but not without crises. Each time, engineers found creative solutions to keep the mission alive. On July 4, 2015, just 10 days before the Pluto flyby, New Horizons went dark. At 1:54 p.m. Eastern Daylight Time, Mission Control lost contact with the spacecraft. No telemetry. No science data. No signal at all. The spacecraft had entered safe mode, an automated failsafe that shuts down all non-essential systems when the computer detects an anomaly. Why this was critical: the spacecraft was approaching Pluto at 31,000 miles per hour. In 10 days, it would scream past the dwarf planet. If New Horizons remained in safe mode, it would miss the entire encounter, 9 years of travel wasted. The automated solution, New Horizons' onboard fault protection system, had detected a timing conflict when the computer tried to compress stored science data while simultaneously preparing for the upcoming Pluto encounter sequence. The computer correctly determined it couldn't do both tasks simultaneously with the available processing power, so it entered safe mode and waited for instructions from Earth. The resolution: engineers spent 90 minutes diagnosing the problem via radio signals that took 9 hours round-trip to reach the spacecraft and return. They uploaded commands telling New Horizons to exit safe mode, abandon the data compression task, and resume Pluto encounter preparations. By July 7, the spacecraft was fully operational again. The crisis had cost 3 precious days of approach observations, but the flyby itself was saved. In May 2018, as New Horizons approached Arakath, engineers noticed the spacecraft's star tracker, the camera that identifies star patterns to determine the spacecraft's orientation, was producing increasingly unreliable readings. The star tracker had been operating continuously for 12 years in the harsh radiation environment of deep space. Cosmic rays had slowly degraded its CCD sensor, creating hot pixels that the computer sometimes misidentified as stars. Engineers spent months developing a software patch that would filter out the hot pixels and improve the star tracker's reliability. The patch was uploaded to New Horizons in October 2018, just 3 months before the Arakath flyby. The spacecraft successfully used the upgraded star tracker to navigate the encounter with perfect precision. Looking ahead to 2028 to 2029, when New Horizons is projected to exit the classical Kuiper belt, engineers anticipate the RTG will be producing around 165 watts, barely enough to power the spacecraft's essential systems. The mission team has developed contingency plans to operate with even less power. The proactive solution: NASA has already uploaded software that will allow New Horizons to operate in an ultra-low power mode, shutting down everything except the computer, a single science instrument, and a minimal transmitter configuration. In this mode, the spacecraft could potentially continue transmitting basic heliophysics data into the 2040s. The expected extension, if power management continues to work as planned, New Horizons could remain operational until the late 2030s, over 30 years after launch. But that timeline assumes no major system failures and continued NASA funding for mission operations. The challenges are ongoing. Each year brings new obstacles. Star tracker degradation requiring software workarounds. Cosmic rays flipping bits in computer memory. Power decline forcing difficult decisions about which instruments to keep active and which to shut down permanently. But each year, New Horizons continues its journey deeper into the Kuiper Belt. In September 2023, NASA announced that New Horizons would be extended through the end of this decade, with operations managed jointly by the Planetary Science and Heliophysics divisions. The specific end date depends on multiple factors: RTG power output, instrument health, and, most critically, NASA's annual budget allocation. In the proposed 2026 federal budget, the White House recommended cutting funding for New Horizons, restructuring the mission to focus exclusively on heliophysics and dismissing the planetary science team. This would end Kuiper Belt object observations and terminate one of humanity's only active missions exploring the outer solar system. The mission's future remains uncertain as of January 2026. Best case scenario, full funding continues, and New Horizons operates until 2038 to 2040, studying dozens more Kuiper Belt objects and potentially even performing another close flyby if a suitable target is discovered. Worst case scenario, funding cuts force mission restructuring in 2026, ending planetary science observations while the spacecraft is still healthy and capable. Most likely scenario, New Horizons continues in a hybrid mode through the late 2020s, balancing Kuiper Belt observations with heliophysics measurements, until RTG power decline forces a gradual shutdown of instruments one by one in the 2030s. Let's calculate the time remaining. As of January 2026, New Horizons has been operational for 20 years. Projected mission end, 2038 to 2040. Time remaining, 12 to 14 years, at most. After that, we lose our only active emissary in the Kuiper Belt. We lose the only spacecraft making detailed heliophysics measurements from the outer heliosphere. We lose a functioning observatory positioned in a region of space no other craft will visit for decades. The connection is finite. The power is declining. And there is no refueling mission that can extend it. New Horizons launched in 2006 with a planned primary mission duration of 9.5 years, enough to reach Pluto and transmit the data back to Earth. It has now operated for 20 years and counting, more than double the original design life. Let's compare New Horizons' technical specifications to modern equivalents using massive ratios. The spacecraft's main computer, a Mongoose V processor, operates at 12 MHz with 8 MB of RAM. A modern iPhone 15 operates at 3,460 MHz with 8 GB of RAM, 290 times faster with 1,000 times more memory. New Horizons' total data storage capacity is 16 GB across two solid-state recorders. A standard 2026 smartphone has 256 GB to 1 TB, 16 to 62 times more storage than a $700 million spacecraft. New Horizons' LORRI camera captures images at 1024 by 1024 pixels, roughly 1 megapixel. The cheapest smartphone camera in 2026 captures 12 megapixels or more, 12 times the resolution. And yet, this ancient technology, this relic from the age of flip phones and dial-up internet, has achieved something no modern spacecraft ever has. It revealed Pluto and the Kuiper Belt in exquisite detail, transformed our understanding of planetary formation, and continues gathering data from the most distant frontier of our solar system. Here's the paradox: obsolete technology, furthest achievement. In 2026, New Horizons will reach $63 from the Sun, traveling at 32,000 miles per hour, $3.10 farther out every year. It will continue measuring the solar wind strength, the galactic cosmic ray intensity, and the dust environment as it travels deeper into the transition region between the Sun's domain and interstellar space. And it will continue to travel through the Kuiper belt, through the scattered disk, through regions we have no detailed maps of, carrying humanity's curiosity as its only fuel. Long after its RTG can no longer power the transmitter. Long after the last signal is received. Long after everyone who built it has retired or died. New Horizons will keep flying through the outer solar system, a silent monument to exploration, carrying a piece of Clyde Tombaugh's ashes toward the stars he spent his life studying. Forever.